Fine.
I am checking right now. Bear with me one moment to confirm this is live. And we're good to go.
Okay, perfect. Okay, so once again, welcome everyone to this new webinar. I will give a short introduction to today's speakers, and then we will start. So let me share my screen, just a second. Okay, let me go back here on this RPC. So once again, welcome back. Today we are going to talk about a new section that has been implemented in OpenSees. It's called ASDCoupledHinge 3D, developed by Diego Talledo. Diego will be today's presenter. Diego is from the University UAV in Venice, here in Italy. He's collaborating with us from a long time now. Just a brief review. So we are continuously adding new components to OpenSees, well, starting from some years ago from the MPCO recorder, then new shell elements, new material models, and many other things. Today, we'll talk about the ASDCoupledHinge 3D. We will do a pull request of this code just after the webinar, because now we have all the code ready. The documentation is ready. We have a preview of the documentation here, but I want to wait the end of the webinar in such a way that I can put also some extra reference here and also a link to to today's webinar. Okay, so after the webinar, we'll do the pull request. So the source code and the documentation will be in the official repository. And of course, in order to use it, you have to wait for the next OpenSees executable to be compiled. Otherwise, you can grab the source code and compile it by yourself. It's not so complicated. By the end of next week, we will also release a new version of STKO, where you are going to have a tool that allows you to create in a very easy way and the ASD coupled section. And Diego is going to show us today how it will look like. Okay, so we can start. I stop sharing my screen, and Diego, please, you can go ahead.
Okay, thank you very much, Massimo, for your introduction, and welcome everybody. Let me just share my screen so that we can share the presentation. Just 1 second, share. Okay, so you should be seeing the presentation, right?
Yes.
Okay, so as Massimo mentioned, today we will talk about this new coupled hinge phenomenological model that is able to account for PMM interaction. This so suitable for lumped approach for reinforced concrete elements. So before starting, let's just review very briefly. This image is very famous. It's from the NIST report, a guide for practicing engineers. We can broadly, very roughly divide the modeling strategies of, in particular for reinforced concrete, but also for other materials, of course, in lump plasticity on one side, on your left, and distributed plasticity on your right. Let me just see if, okay, I have the pointer. So the lump plasticity can be, for instance, plastic hinges where we have a rigid plastic hinge, or can be more detailed inelastic springs with hysteretic properties. And here you can see several examples of possible phenomena that can be taken into account with hysteretic models. On the right, we have distributed plasticity, starting with the most complex, probably the finite element modeling that requires discretization through the member length and through the cross-section into several finite elements. It's the most detailed one, but of course it requires proper constitutive laws that need to be defined, like for instance the concrete 3D that Massimo briefly showed us before. Then we have the commonly used fiber modeling. Actually, fiber sections are not required for distributed plasticity. We can have also moment curvature constitutive laws in several Gauss points along the member. But anyhow, in its most common implementation, that is the fiber discretization of the cross section, we perform numerical integration through the member cross-section in order to obtain the constitutive moment curvature relation, and along the member length, so permitting the spread of the inelasticity. In this case, of course, we need to define the uniaxial material models in order to capture the hysteretic behavior of the cross-section and hence the member. Of course, we know that the formulation can use displacement or force interpolation functions, but there is a lot of material on that, and we have also several webinars here, so I will not go further into this description. Something in between, let's say, is the finite length hinge, the original formulation proposed by Professor Scott in its very famous paper. Basically, we have a specific integration method along the length of the element that permits to basically calibrate the plastic edge length, so making it more easily controllable respect to the standard distributed fiber section. So summarizing, we have on one side fiber sections that, as we said, are typically used in distributed plasticity. Of course, they have some undoubtedly advantages. For instance, it's very easy to define based on the geometry and the constituent materials, all uniaxial, as we said. And the other big and strong advantage is that automatically captures the interaction between axial force and biaxial bending moments, so PMM coupling. On the other hand, of course, it's computationally more expensive method, and it's somehow more difficult to include secondary effects like bar slip, buckling, cyclic degradation, etc. Of course, there is a lot of literature, there are a lot of papers out there that deal with these specific topics and that tries to include these aspects, maybe with specific hinges added or some other strategies. So it can be done, but it's not super easy and it's not so comfortable. The other thing is that it can be sometimes difficult to interpret the strain demands computed by the analysis in terms of acceptance criteria. These criteria are more widely reported in terms of rotations. On the other hand, we have phenomenological hinges that, as we have said, are typically used in lump plasticity modeling. For sure, they are computationally more efficient. It's easier, at least, to include all these secondary effects like bar slipping, buckling, sulfate degradation, etc. Of course, on the other hand, this requires a proper calibration of the hysteretic law, and this is not always a simple task. And it's also easier to interpret the results in terms of acceptance criteria because we have the results in terms of rotations. On the other hand, we have two strong problems. The first problem is that typically these hinges are composed of uncoupled springs and doesn't account for PMM interaction. Of course, you can do something in your model. You can, for instance, calibrate each hinge based on the axial force that you have after the static analysis of the gravity load, or you can do something like that. But there is no real coupling between axial force and bending moment during the analysis, and the axial forces can change during the analysis. The other problem is that we should calibrate each hinge for each section of our model. So if we have several sections in our model, we should perform proper calibrations for each one of them. So the objective of the model and the tool that we are presenting today is somehow to try and tackle these two aspects. So first of all, we developed a new phenomenological hinge model with the PMM interaction. This is done in OpenSees, so it means that you can use this model independently from STKO. On the other hand, on STKO, we developed a tool to easily define the hinges from the section geometry and the constitutive materials. So these constitute our new ASDCoupled hinge model. So how can we describe very briefly the idea? The idea is starting from the uniaxial materials for the individual degrees of freedom. In the current version that we are presenting today, for axial degree of freedom, torsional degree of freedom, and the two shear degrees of freedom, we are adopting a penalty approach. So we are using an elastic material with a high stiffness. For what concerns the two bending degrees of freedom, we are using an hysteretic material that is the pinching for material that you can see in this picture on the right. Then we use a strength domain to define the interaction between these forces. And the idea is combining these two informations in order to scale the material's backbone, of course, for the bending degrees of freedom, as you can see in this picture here, very schematically, of course, for every step of the analysis. So this is basically the idea. I'd like to say some more words about the strength domain, the PMM strength domain. The strength domain is provided by the user and can be provided as a structured list of triplets, so P, My, and Mz. In particular, we are referring to a cylindrical coordinate system that is centered in 0, 0, 0, and whose longitudinal axis is aligned with the axial direction axis. If we define n divisions along the axial force and n theta divisions in theta, that is so on the My Mz plane, where it's counterclockwise and starting with 0 at My positive and Mz 0. We provide in this structured way the list of triplets PMM. And I will show you shortly an example to be more specific. Then the domain is internally stored in a structured mesh. And then for each step on analysis, the ray of the trial internal force vector, so P star, My star, and Z star, with the origin on the slice that we are considering, that is the P star slice, is intersected with the mesh domain. So we find intersection points for the required direction, and then we update accordingly in terms of strength the backbone curves for My and Mz. So basically, the coupling is done with the internal forces at the previous known time step. So there is no iterative coupling. We have a diagonal matrix of stiffness, and the coupling is updated explicitly, basically, each time we have convergence. So each time we commit the current step. What about the deformations, so the rotations? Well, actually, we have for initial stiffness, pre and post cap rotations, we have many formulations available in literature for the sake of of an example. I reported here some diagrams for initial stiffness, cap rotation capacity, and post-cap rotation capacity proposed by Hazelton in 2016. But there are a lot of formulations out there. Think about FARDIS, for instance, and many, many more. So we were thinking about implementing one or more of these relations when we decided, in order to give the user maximum flexibility, so the possibility to test different relations or even define our own relations in our research, we decided to use a more flexible approach using Tickle expressions. So basically, this is the command in OpenSees for the ASDCoupledHinge 3-dimensional. We have several parameters. As usual, as a convention, those within these brackets are optional parameters. So we provide some default parameters for those. The others are mandatory parameters. So the first parameter are basic parameters for the section. As I named before, we of course need a unique tag identifying the section, but we need also the penalty stiffnesses for axial, torsional, and the 2 shear degrees of freedom. Then we have those Tickle expressions that I mentioned for the initial flexural stiffness, the cap rotation, and the post-cap rotation. So these Tickle expressions permit to use placeholders like N, M, and V for respectively for the internal forces, axial, moment, and shear. And as you can see here in this example that we will comment better later, so don't be afraid if it's somehow a little bit mistake. Those placeholders will be recognized by OpenSees and will be replaced by the associated value of the internal forces inside the coupled hinge at the current step of analysis. Even we can define our proper Tickle procedures previously. I will show you an example. And so we can even access previously defined Tickle procedures. Then we need to define the strength domain, as I mentioned before, and we are permitting 2 possibilities, basically. So one, and they are alternative. The first one is strength domain by points, where the user gives the number of discretizations along axial and along theta, that's the angle that I mentioned before in this cylindrical coordinate system, and then provides the list of N, M, and M for creating this structured mesh. Of course, this can be somehow complicated. We will see later that in STKO we developed an utility that creates all of that for us. Another possibility that maybe it's more simple as an input is the simple strength domain, where we need to provide just 5 values, and those 5 values are the minimum value of axial force, sorry, the minimum is here the compression, the maximum value in tension of axial force, the 2 maximum moments, and the value of N of axial force for those moments. What we are doing in this version is a simplified domain on the safe side with a linear interaction domain, basically. So we're creating this sort of diamond-shaped domain. Of course, we will obtain results on the safe side, as you can see clearly from this picture, where we are comparing schematically a accurate domain versus a simplified domain. Then we have the definition, it's optional, as I mentioned before, of the hysteretic rules. Those are basically the parameters of the pinching for model. So we have the parameters that define the hysteretic rules, the usual parameters known for those of you that used already the pinching for model, and the parameters that control the damage of the envelope, the damage of in the loading stiffness, and the damage, the degradation of the reloading stiffness. I'd like to mention at at this moment that for now we implemented this model with the pinching for hysteretic model, but for sure we will add more models like the hysteretic model, the Ibarra-Medina-Krawinkler, etc. So what about the STKO preprocessor implementation? So we defined a specific X object where we can input all those parameters. It's defined basically by standard fiber section. We need this fiber section in order to compute the interaction domain. And it's used just for that. So it's used internally in STKO just in the moment we are generating the TCOL files. Inside here, we can have several advantages, like, for instance, the automatic consideration of confinement, etc. And it's worth mentioning that the TCOL expressions that you can see somehow here for the hinge parameters are a little bit more powerful here respect to the poor TCOL OpenSees counterpart, because here the users can access extra variables like the geometry variables, like the gross area, the width, the height of the section, etc., or material properties, like, for instance, the compressive strength, etc. So we can have access also to these placeholders. Those placeholders will be substituted by STKO in the moment that it's writing the TCOL files. So in the TCOL files, we will not see these sort of placeholders, of course. So now I would say that it's demo time, so I can show you something. Let me just ask from the presentation. I'd like to mention that you will find a folder downloadable from the website, and here you will see some files and some examples that we will see together right now. So I will show you those files, and you can later on maybe try on your own. So the first example that we are trying to do is basically two stage analysis. In the first stage, we apply axial load that then is maintained constant and apply a lateral load. So the file that we will use is the first file, where you will find two Python files and the STKO file. So I already opened this file for you, and you will see basically this file. In this file, what I created two geometries for two columns. I will show you just in a second the details of the geometry. From the property, you can see that this element on your right is already defined. Basically, this is the column modeled with the classic fiber approach, actually with the finite length hinge approach. And so you will see the model that it's already at this stage. And we prepared the geometry for the hinged approach, and we will create it together right now. So basically, what example are we trying to simulate? The geometry is the geometry taken. I'm showing you the peer structural performance database. The Tanaka and Park test on a column, the number 5 and the number 6, actually they are basically the same. You can see we have the material properties is 32 megapascal for concrete and 511 megapascals for yield stress of the longitudinal bars and 325 for yield stress of the transverse bars. The section is 55 centimeters by 55 centimeters, and it's 1.65 meters high. The axial load is around 1,000 kilonewtons, so having an axial loads ratio of 0.1. And we have 12 bars, all with 20 millimeters in diameter, with a clear cover of 40 millimeters. So this is the example we are trying to simulate. First of all, how do we model this this column? Well, let me just briefly show you a couple of slides more. So how can we model with lumped inelasticity? This should be quite known to most of you. Basically, we concentrate inelasticity in this nonlinear hinge. The typical way of modeling this is basically considering the element and the hinge in series. So the total response is represented by this m theta graph that can be tau as composed by the elastic element whose stiffness is usually the effective stiffness, so not the gross stiffness, plus the behavior, the plastic behavior, basically, of the nonlinear spring. Here it's represented in terms of moment and plastic rotation. So we use a very high stiffness initially, and after the reaching of the yielding moment, we start basically using our hinge. We can use this approach with the ASDCoupledHinge, and for instance, we can estimate the effective second flexural stiffness according to, for instance, HSA 41, where we have the well-known values. These values doesn't depend directly on the axial load. Of course, they depend in the sense that when we have a small gravity load or a higher gravity load, we have different values. But we can use something a little bit more detailed. For instance, just for the sake of simplicity, as I said, you can implement your own equations. This is the power of this hinge. This is the equation proposed by Hazelton in 2016, where we can see that there is a dependency on axial force and on shear span. How can we do this with our hinge? Well, we can do something like that. We can consider that the elastic element, we model it not with the effective stiffness, but with the uncracked stiffness, so the gross inertia. And again, the usual relations, we have a system in series, so the inverse of the total stiffness is the sum of the inverses of the stiffness. We can estimate the, sorry, I'm seeing that you are not seeing probably the pointer. We can estimate the stiffness of the elastic element, of course, with the gross inertia. The total system stiffness is the one related to this equation here. So I just factor out in order to have this coefficient here that will be represented by this equation. And the stiffness of our spring element, that is a zero-length section, it can be shown that it's related basically to the rotational stiffness. This is the stiffness that we need to input in our model that we will input right now. Okay, so we can compute this value here, and so we obtain that our rotational stiffness of the hinge is equal to this expression here. Okay, so it's accounting that it's a series system, so it's accounting for the length, it's accounting for the Hazelton stiffness, and for the gross stiffness. Okay, so going back into our model, what do we need to do for this? I will do this very quick. We need to create first of all, our materials. Our section, our ASDCoupled section, used simplified materials, design materials, let's say, that are basically the constitutive laws used for design purposes. So we will define a concrete FC. We said that it's 32 megapascals, and we find these materials in uniaxial design. We have concrete and steel. So we define a concrete. Here we define in a simplified way the materials, and we can have directly the properties for different classes of concrete according to model code, Eurocode, or whatever. It can also account for the fact that the concrete is existing or not, but in this case, we're just using a custom value of 32 megapascals with 32,000 of elastic modulus. Okay, so the concrete is defined, and we have to define our steel. So again, uniaxial design steel, we give a name to it, and we have said that it's 511 megapascals. The ultimate strain that is needed for finding the strength domain, we assume it's 6.75% and 206,000 megapascals. Okay, so we defined our steel. So now we can define our section, and I will show, sorry, not the definition. So right click on physical properties, add, and here we create our PMM section. We will find this section in sections as the coupled hinge rectangular RC. Okay, so we are defining a rectangular reinforced concrete section. We just input very quickly the dimensions. This was the clear cover, and we say that it is 20 millimeters bars, 2 bars per side. Okay, so 2 bars here and 2 bars here. Then for the materials, in this case, I don't want to account for confinement effect because it's not so relevant for the strength domain. And so I input the same concrete simplified in cover and core, and I input the steel. I don't need to include, of course, the stirrups, so I leave the default values because this is generally needed for automatic calculation of confinement. I'm okay with these values of penalty stiffnesses, and we need now to input the hinge parameters. Okay, so here we need to input some equations in valid Tickle expressions that will be evaluated at each step by OpenSees. So as I mentioned before, permit me to press OK and keep it saved like that. As I mentioned before, we can use previously defined user functions. So you will find in the file a definitions for hinge X object that inside contains some Tickle code. And here, this Tickle code is a procedure for returning LV over H, so the shear span over H of the section. We have 3 input parameters that are M, V, and H. And the procedure for accounting for the fact that the system is in series. So basically, given a coefficient in input, here I implemented the equation that we have seen just a moment ago in PowerPoint. Okay, so in our section we can use those previously defined functions because Tickle now knows those functions. In order to simplify ourselves, you will find in the material a file that is called hinge parameters, okay, where for each one of the parameters I already written the Tickle code. To comment this, you will see that this is exactly the equation proposed by Hazelton. So these are the terms. We have the placeholders that OpenSees recognize, plus the placeholders that OpenSees doesn't recognize, but are recognized by STKO. So you will see that we will not see in the final Tickle file this expression here, okay? Because just N, M, and V are recognized by OpenSees. Okay, so I just copy paste these equations here. I copy paste also the other equations. We have the relations as placeholders. We have my, mz, vy, vz, etc. If you just write v and the m, it automatically understands what are the needed values independent on the direction that it's considering. So this is done automatically by STKO, okay? And by OpenSees, of course. And I don't want to touch hysteretic parameters that are all optional because we first will perform a monotonic load test. So basically, we created our simplified section. We need to create also the elastic section. This is very easy, section, elastic section, and we create a box shaped with 55 centimeters, sorry, and 55 centimeters. Make sense? The elastic modulus of concrete and the shear modulus of concrete, and I call this elastic section. I don't need to apply a modifier, stiffness modifier, because we said that the elastic element in the approach that I'm using right now, that I'm showing you right now, uses the gross stiffness, the stiffness of the gross section, sorry, okay? So we define the elastic section. We need to define the physical properties for the integration of the elastic element. So we use beam column and beam section property. So this is the beam integration physical property. This is for the elastic element. So we use the elastic section. A standard Lobato is fine since the element is elastic. Okay, and we now define finally the last component of the physical properties, that is our hinged beam. The hinged beam, as you know, it was already presented by previous webinars. Sorry, it's hinged beam. It requires the physical property of the main beam, that it's our beam integration, and it requires the zero length section, the zero length material or the zero length section for I and J node. In our case, we are modeling a cantilever, so we just need at the bottom node our newly defined PMM section. So that's all. In this way, we apply the hinged beam to our element. And you can see, as convention, we adopt that where there is an hinge, we have this sort of offset or shrink, I don't know how to call it, in the element. So everything is well defined. We still need to define the element property, as you see from this transparent background. For defining it is very, very easy. We first need to define our zero length section. And it's a zero length element, zero length section. Here we just have to give the information about the dimension. So it's just 3D. And as you may already know, the hinged beam element property. So here we have a special purpose, should be, yes, hinged beam. The main beam is a force beam column. The bottom node has a zero length section. And the game is done. So we select the element and transfer also the hinged beam. So we have both physical properties and element properties defined. Okay, I just saved the model. You will find that the file already has the boundary conditions. So basically we constrain, as you see here, we fix the two bases and we fix the top nodes in order to maintain the displacement in the two dimensions, so in the plane. It's not mandatory, of course. Then we apply an axial force. In this case, I applied 1,000 kilonewtons of compression, so similar to the value that I've shown before from the Tanaka experiment. And we apply an horizontal displacement. I select the 200 millimeters as my reference value. And you will find all the analysis steps already prepared. So we created the recorder. Here you can record every quantity that you prefer. We apply the constraints, we apply the vertical loads, and we perform the vertical analysis. Then we add our horizontal load pattern. I've added a couple of monitors. One monitor is for the hinged element, and the other monitor is for the fiber element. Okay, they should be, one is called fiber, the other is called hinge, and I set the parameters for the horizontal analysis. Okay, so say that we can just run our our file. It asks me where to save it, and you will see that it's processing. Behind the scenes, it's computing the strength domain. And let me show you also, well, now it's running. It would take not so much time to run. So, but meanwhile it's running, let me show you a couple of tools, nice tools that we included in the fiber section widget that I didn't show you before in order to wait that it was running. Sorry, not this one, our simplified section. If you pay attention before, there is a test button down here. If we press test, STKO will compute ultimate and yielding domains, interaction domains. It will take some seconds. Okay, it computed the ultimate domain, then it's iterating the strings to compute the yield domain. Okay, now it's a little bit slower because running on the other parts. So this is the tool that we developed to inspect our results. So we basically have our three-dimensional domain, N, My, Mz. We have two sections in the planes N, M, so uniaxial bending, say it differently, and we have the MM slice. Here we have some tools to inspect our domains. So we have a slider that permits us to slice this domain along different values of n, and we see which one is the slice domain. We can always pressing this button returns to n equal to 0, and we can set our own value. For instance, I'm going to 1000 kilonewtons. That is the analysis that is doing exactly now. Then you can see a button that is called data. This button contains the numerical data that you can copy paste using Excel and whatever for the NM, NM, so the two planes, plus our MM plane. It's written within brackets for the n value that you are using. So if I change my n value here, you will see that the data will be updated accordingly. So I can copy paste this data and use whatever I like. Then we included this button here that is a sort of a fiber inspector. So it permits, if you press and keep pressed it, you can press on whatever point of this domain you want. For instance, I click here, and it will show you in this red point the distribution of strains and the distribution of stresses for steel and concrete with two different color bars. So we can inspect the values and have an idea of the distribution of strains and stresses that we can use. In these tabs up here, we have the ultimate NMM domain, but we also have the domain in terms of axial force versus ultimate curvatures. Okay, also here we can slice, we can inspect, we can zoom, we can do whatever we need. And we have the domains in terms of forces for yield conditions and the curvatures for yield conditions. Okay, so this is an inspection tool that we developed. Meanwhile, the analysis should be finished, and here we can compare the result of our fiber and our hinged model. What if we want to see how this model works for different values of n? So you will find in the material also a Python file that is called parametric n constant. If you open this file, you will see that it's already set for doing a parametric analysis for different values of the axial load. I will not go into the details of this file. There is another couple of webinars that uses this kind of approach, so you can go and be referred to them if you want to see more, but you will find this file so you can expect a little bit more on your own. So if we run this file, what will happen? It will happen that here we are, it's creating some folders. Here it's creating the folder with axial force 0, and in some seconds it will create also the other folders, so 500, etc., etc., etc. Meanwhile, it's solving and creating. I'd like to show you the TCOL code that was written by STKO. So if we open it in Notepad or something similar, we can see here that it created for us, of course, it created the confined version for the automatic confinement computation for the fiber approach. We didn't use confinement for the hinge approach. Okay, and this is our fiber section. I close it. And then we have this structure domain that I mentioned before. So you see, it can be quite cumbersome to insert these values in OpenSees. So STKO has this big advantage that creates for us N list, MY list, and MZ list. And this is our OpenSees code for creating our section. So this section contains the parameter that we mentioned before. We have, in this case, sorry, meanwhile it's running, so let's just make it run. It's running in parallel all the values of n. So while it's running, let me comment further this. So we have these parameters defining our strength domain by points, and we have our expressions inserted. As you see here, the placeholder for the gross area of concrete or for the strength of concrete has been replaced by STKO. So this is perfectly legit OpenSees code. So these are the placeholders that OpenSees will recognize. So this is how this section is created, and we will come back in a second to this. Meanwhile, it's running. We can compare here the responses. In this graph is not super clear, but I will show you in a second file that it's much more clear. The responses for the different models. So let me close meanwhile the solutions. Okay. Here you will find another Python file that is for plotting the result. You can just run here on in your own Python environment. And here is the response. As you can see, our hinge is able to capture the difference that we observe also experimentally in terms of strength, but also in terms of utility. We see that, for instance, the peak rotation is reduced with increasing of axial load. We can see also the change in the initial stiffness, in the flexural stiffness. For increasing value of n, we have increasing value of stiffness. These three values of n has the same stiffness because in the relation of Hazelton there is a bound, a lower bound, and so they are all with the same lower bound. But of course, anyhow can implement its own equation, so no worries at all. I would like to show you something a little bit similar somehow, and I will show you just maybe one example, but you can do more of them. I copy paste this folder here in this simplified domain. So this is our version that we just run, and I take all these TCOL files that were created by STKO, and I create a new folder that is called simplified, for instance, and I passed it here. Okay, what I'd like to show you is that, for instance, if you don't have STKO or don't want to use STKO, you can, I will delete of this and I will use the simple strength domain. I hope I didn't do any typo. And what are the parameters that we need to provide here? Is the minimum value of axial load, so it's minus 1.12 e to the 7. I've already computed them separately, of course. The maximum value of axial load, the maximum values of moments in y and z direction, 9.2 e to the 8, and the value of n of axial force corresponding to the maximum values of the moments. Okay, so it's as simple as that to have already a coupled section, even if simplified. So if I run now my solution, okay, it should be pretty fast. And let me just copy for doing a quick comparison. Sorry, I didn't need it before. Let me just copy a monitor, for instance. Okay, I put it here so that we compare these two responses. Okay, let's don't look at the fibers that are the same, of course. Comparing them, of course, the simplified, sorry, I didn't change the name, the simplified is the red one, is a little bit lower because we have a linear interaction domain. So we have results generally on the safe side. But on the other hand, it's, as you can see, very, very simple for definition. So moving toward the end, I'd like to comment a little bit more this graph here. One may wonder why fibers generally show a peak that is more towards the left respect to the peak that is shown in the hinge. For answering this question, we created a model that is very similar. Let me save and open another model. It's very, very similar. You will find in the material, not the simplified domain, sorry, this folder here with constant n but cyclic tests. And here we are simulating the actual test of Tanaka. I split it for convenience in two separate files, one for fibers and one for hinged. And comparing the results, I also shown you cyclic and monotonic load for doing some comparison. So let me just open, for the sake of example, sorry, not a Python file, an STKO file. Okay, the hinged version cyclic. So respect to before, it's basically the same model. We just changed our simplified section, and we included in this section some betterly calibrated hysteretic parameters, so the known recovery displacement, recovery force, and unloading force, both positive and negative, plus some other parameters of damage. In this way, I will not run this for you right now. In this way, we were able to obtain this response that I will show in a second. So the response should be here. Let me make comparison between a fiber model here on the left and the hinged model here on the right. Okay, so this is the comparison that we want to do. You will see both monotonic and cyclic, and for the cyclic, you will see two distinct monitors that I created because there are two beams that actually represent two specimens, basically. So here is the comparison between the fibers on our left and the hinged on our right. Let me try to enlarge a little bit more. Okay, perfect. So what can we see here? Well, we can see that even if the monotonic peak is on the right here at 120 something millimeters, due to the cycle degradation, we can capture the envelope, the experimental envelope, as you can see here. For the fibers, at least let's say for vanilla fibers, for the very simple models, of course, something better can be done, calibrating better the steel, and of course it's true. But you can see that the cyclic strength degradation is a little bit more complicated to model, and it may be that just a better reinforcement does it, but some of these aspects are related to sleep or to other stuff, so it's complicating the modeling. Here we can somehow calibrate these rules to obtain a satisfactory response. How can we calibrate these? With trial and error or with other strategies. We are working right now in ASDA in implementing a genetic algorithm. We are testing it actually for calibrating automatically these for the user. So the user will provide a constitutive of an experimental curve, and we will try to perform the best calibration out of it. Okay. So we are basically out of time. So let me very, very briefly show you the last example that I included. That is a variable axial load action. So what have we done? Sorry, here. Let me open this new file that you will find in the material in the next days. It's basically a model very similar to the ones that you have seen before. Here there is something different. You will see a variable time series for the axial force. And if we inspect it, we will see that we have this sort of amplitude increasing axial force that will act in the same moment as the lateral load. So to show you a picture that I included in the material is something like that. So the lateral displacement is increasing linearly, while the axial load is increasing with this increasing amplitude cyclic history. So just to don't run and waste your time further, you can inspect the model on your own, of course. Let me show you just the results. I will use just my Python interpreter here. And I already included the Python file. It's called plot results for doing the plot. Here, for the sake of simplicity, I have done for just one value of axial load that was equal, if I remember well, to 4,000 kilonewtons. Let me just check. 6,000 kilonewtons. Okay, so I have 6,000 kilonewtons of axial load, and here you can see the force displacement relation comparing the fiber approach with the hinge approach. I like to say that the hinge approach cannot and doesn't want to be as accurate as fiber approach in general. So if one needs something very detailed, have to perform a very detailed finite element or fiber modeling with those other kind of springs or hinges or whatever for accounting for all the effects that want to account. But it wants to be quite accurate, so sufficiently accurate, but in the same time computationally inexpensive method. Okay, so just for concluding, we presented in today's webinar a new phenomenological hinge section that you will be able to use very soon from the next compilation of OpenSees in OpenSees, and with some utilities in STKO. Our PMM interaction is accounted both for moments, so a scaling of the strengths, but also for rotations with the use of the Tickle expressions that give to the user maximum flexibility in implementing its own hinge properties. What are the feature developments? Most of them already work in progress. Of course, as Massimo mentioned before, we are ready to submit the pull request to OpenSees and the OpenSees documentation repos. We want to improve the graphical user interface in STKO for an easier management of the different expressions. Right now, I've shown you that you have to write your expression in Tickle, and this can be quite cumbersome for some users. We are developing a new tool that will have a list of expressions. You can create and add your own expressions so that you can easily select and interchange them during inspection and during research. We want also to address the extension to the Python interpreter, because as I've shown you, we started implementing this when the Python interpreter was not still so much used. So we developed this with Tickle expressions and Tickle evaluation during the analysis. Then we want to extend the interaction also to shear, so PMM VV, so for accounting also for the shear flexion interaction, and consequently allowing the user to define its own expressions, Tickle or the new versions that we will find for the other degrees of freedoms, like for instance, the shears, so that we can add shear models and so on. So with this, I conclude. I thank you very much for your attention, and I'm of course open for questions.
Thank you, Diego. Thank you for the nice presentation. So yes, we have time for questions, but just a brief reminder, as Diego just said, we are going to do the pull request for the code and the documentation starting from tomorrow, because we need the recordings of this webinar to be online so that we can put a link on the documentation. For users that wants to use this new tool, of course, you have to wait for the official OpenSees to be compiled with these new features. Option 1. Option 2, you can download the latest source code of OpenSees and compile it by yourself. Or during, I think, the next weeks, Professor Tarke will provide an official precompiled version of OpenSees starting from our fork. So you will find in the next weeks this new tool. More or less at the same time, we will release version 4 of STKO, which has many new features, but also this new tool that Diego just showed us. So now we have time for questions, because I've also seen people that were connecting now, probably because of the mistake about the GMT +1 and +2, because unfortunately we still we had a problem about the time. So please, we have time for questions. You can write them in the chat, or you can switch on your microphone and ask directly. Is everything clear? Well, Diego, it seems that it was pretty clear. There is no one with
Okay, if there are no questions, maybe right now, but maybe they will come up when they will test by their own this model. So I'm of course available. You have my address just right here, so I'm available to answer your questions also in the coming days and weeks. to my mail or also to the STKO forum, of course.
Yes. So, okay, if there are no questions, or at least no question right now, I would like to thank you everyone again, and there will be other webinars. The next one will be in May, and we are going to present some other new feature that we added in OpenSees, in particular the new ASD shell T3, which is the triangular counterpart of the ASD shell Q4, based on the same formulation. Basically, it's a thick shell considering out-of-plane shear deformation. Okay, so thank you everyone, and see you on the next webinar. And by tomorrow, you will have the recordings that were live on YouTube, on our website, and the documentation, all the support files created by Diego. So by the next week, when you will release the new STKO version, you will be able to test it out. Okay. So once again, thank you, Diego, and thank you everyone for
Thank you, Massimo. Thank you, everybody.
Thank you, Diego. Thank you very much.
Thank you, everyone.
Thank you.
Thank you.